Meet Stephenson 2-18. If you have heard of it, you know it by its reputation. The undisputed king of stars, a cosmic giant so ridiculously huge that if you dropped it into the center of our solar system, it wouldn't just swallow Mercury, Venus, Earth, and Mars. Its surface would stretch past the orbit of Jupiter and reach all the way out to the Saturn. Light, the fastest thing there is, would take nearly 9 hours to circle it once. Our Sun, light makes the same trip in less than 15 seconds. It currently holds the title of the largest star we have ever found. But what if I told you that the crown is, well, a little wobbly? That its title is built on the foundation of cosmic uncertainty. From our vantage point, which is nearly 20,000 light years away, we can't actually be sure of its colossal size. The story of why reveals one of the greatest challenges in modern astronomy. It's a detective story played across the interstellar space where the biggest star in the universe might not be what it seems. Section 1. Meet the champion. To understand the controversy, you have to appreciate the champion. Deep in Milky Way, towards the constellation Scutum, lies an open star cluster named Stephenson 2. It's a bustling city of stars, home to a whole collection of red supergiants. But one of them, Stephenson 2-18, or ST2-18 for short, stands out from the crowd. Visually, it's not much to look at. Actually, you can't see it at all in visible light. A thick fog of space dust completely hides it from view. We can only pierce through the veil by looking in infrared. And when we do, we see the faint, reddish glow of a true behemoth. The numbers are just staggering. Its most quoted radius is around 2,150 times that of our Sun. If our Sun were a single pixel on this screen, ST2-18 would be a glowing sphere over 7 feet tall. You could cram almost 10 billion suns inside it. If you wanted to fly a 747 around its equator, that trip would take you more than 1,000 years. This is the scale we are talking about. A star so big, it blurs the line between the Sun and the entire solar system. The title of largest star is a notoriously shaky one. For years, the crown belonged to other supergiants. Before that, names like VY Canis Majoris and WOH G64 were in the running, but the list is always changing. In fact, the same kind of analysis that pushed Stephenson 2-18 to the top is what that demoted the old king, UY Scuti. More accurate distance data revealed UY Scuti was probably much closer to us and therefore smaller than what we thought. And just like that, a new monarch was crowned. It became a new benchmark for the cosmic scale. But in science, every king faces scrutiny, and the reign of Stephenson 2-18 is far from secure. The numbers are impressive, but they're also where our mystery begins, the cracks in the crown. Here's the thing about science. It's not a book of facts, it's a process of asking questions. It's about relentlessly changing what we think we know. And when we start asking questions about Stephenson 2-18, the crack begins to show in its supersized crown. The main problem is simple to say but incredibly hard to solve. You can't really measure the size of something that is 19,000 light years away directly. There's no cosmic measuring tape. Instead, astronomers have to be detective, piecing together clues from a faint light that traveled for millennia to reach us. The basic recipe for calculating a star's size comes down to two things: its temperature and its luminosity. The temperature is the easy part. We can guess it from the star's color. Cooler stars glow red, hotter stars burn blue-white. Stephenson 2-18 is a deep, cool red with a surface temperature of only about 3,200 Kelvin, barely half as hot as our Sun. The second ingredient, luminosity, is the tricky one. Luminosity isn't how bright a star looks from here, that's apparent brightness. Luminosity is how bright the star actually is, the total energy blasting into the space. There's a beautiful bit of physics called Stephenson-Boltzmann law that connects all of this. Basically, if you know the star's total energy output, that is luminosity, and its temperature, you can calculate its total surface area, which gives you its radius. Simple, right? Measure temperature, measure luminosity, do the math. But, and here's the giant but that kicks off our whole investigation. Both of those measurements, especially luminosity, are filled with huge and potentially deal breaking uncertainties. To find a star's true luminosity, we need to know how bright it looks and its exact distance. And it's right there, in the vast emptiness between us and the star, that our solid numbers start to dissolve into fog of doubt. Our cosmic detective story begins now, and first piece of evidence is to examine the star's address. Because if we don't know exactly where it is, we can't know what it is. Imagine seeing headlights on a dark road. Is it a car with a dim light around the corner or a huge truck with brilliant high beam miles away? It's impossible to tell without knowing the distance. That's the exact problem astronomers face. For example, look at these two stars. They look near about same from our perspective, but star 2 is tens of thousands times more massive than our sun and at least 20 times bigger. And star 1 is much more like our sun. To figure out star's true luminosity from how bright it appears, you have to know precisely how far away it is. Light intensity drops off with the square of the distance, so a small error in distance can create a massive error in its calculated size. And this is the single biggest problem of Stephenson 2-18. Our best guess puts it at about 19,000 light years away. But that number comes with a giant catch. The official uncertainty in that distance is greater than 50%. Think about that. The star could be thousands of light years closer to us or thousands of light years farther away. If it's closer, its luminosity plummets and radius would shrink dramatically, knocking it right off the top spot. But if it's farther away, it would have been even more luminous and even larger, pushing it into territory that seems physically impossible. The whole claim to the throne rests on this one very shaky number. Challenge 2. The case of mistaken identity. This brings us to the next question. Why is distance so fuzzy? Well, that distance measurement isn't even for Stephenson 2-18 directly. It's an estimate for a star cluster it's assumed to be part of Stephenson 2. A star cluster is a group of all stars born from same cosmic cloud. So we can assume that they are all at same distance. This is a vital shortcut for astronomers. But what if Stephenson 2-18 isn't actually a member of the club? This is a hot debate. Some studies show that its movement, the speed at which it's traveling towards or away from us, doesn't quite match the other stars in the cluster. Some astronomers argue that because of its outlying position and weird properties, it's probably just a random star in the foreground or the background that happens to be in our line of sight. If it's not part of the cluster, then the whole reason we use that distant estimate is wrong. We would have no reliable way to know how far it is. It would be a cosmic lone wolf, its true size a complete mystery. The case for largest star would collapse. Okay, let's give it the benefit of the doubt. Let's assume that it is in the cluster and the distance is right. The problem don't stop there. The space between us and the star isn't empty. It's filled with a thin but persistent smog of interstellar dust and gas. This cosmic fog causes something called interstellar extinction. Just like a fog on Earth makes distant streetlight look dimmer and redder, this dust does the same thing with starlight. And Stephenson 2-18 is one of the dustiest, grimiest part of the galaxy. To find its true luminosity, astronomers have to guess exactly how much of its light is being blocked. This correction is as much as an art as a science. A dust isn't smooth, it's clumpy. Our models are good, but they aren't perfect. Different models spit out different results. In fact, different studies have produced wildly different luminosities. While the most famous study puts it at stunning 440,000 times the sun's luminosity, another calculation comes up with much more modest 90,000 times. That huge gap shows just how tricky this is. A different dust correction means a different luminosity, which means a very different size. Finally, our investigation turns to the suspect, the star. Red supergiants aren't the neat, perfect spheres you see in the textbooks. They are violent, chaotic, and unstable beasts. They don't have well defined surface. Instead, they have incredibly fuzzy, extended atmospheres that boil and churn into massive scales. Just figuring out where the star ends and the space begins is a nightmare. On top of that, these stars are constantly blowing off their outer layer in powerful stellar winds, creating a cocoon of dust and gas around themselves. So, it's a star wrapped in its own personal fog, on top of a galactic fog that's already in the way. This self made dust cloud makes everything even more complicated, obscuring the star's light and making it incredibly hard to get an accurate temperature, which just adds to another layer of uncertainty to its final size. So, to recap, the star's distance is a huge question mark. Its membership in its own cluster is up for debate. Its light is blocked by who knows how much dust, and its own atmosphere is turbulent, fuzzy mess. That neat calculation we started with has become a pile of compounding uncertainties. Alright, it's a cosmic detective story with no easy answers. When you weigh all these challenges, what do you think is the single biggest hurdle for astronomers trying to measure these giants? The distance, the dust, or the nature of the star itself? Let me know your thoughts in the comment section below. After sifting through the evidence, or lack of thereof, we have reached the final phase, the theoretical showdown. This is where we compare what we see in the universe with how we think it's supposed to work. This is where Stephenson 2-18 goes head to head with the laws of stellar physics. For decades, astronomers have built complex computer models of how stars evolve. These models are basically the official rule book for the stars. They predict how a star of a certain mass should live, burn fuel, and die. And these models predict there is a limit to how large a star can get. This theoretical ceiling, sometimes called as the Hayashi limit, suggests that for a red supergiant in our galaxy, the absolute maximum size should be somewhere around 1500 times the radius of the Sun. Any bigger, the star would become so unstable that it would literally tear itself apart. And this is the ultimate conflict. The most popular measurement for Stephenson 2-18 is 2150 solar radii. That isn't just a little big number than the theoretical maximum, it's stubbornly and fundamentally bigger. Its estimated luminosity of 440,000 suns also pushes the absolute upper limits of what our models say is stable. This creates a fantastic dilemma. There are two ways this can go, and both are profound. Possibility A: the measurements are wrong. This is the simple answer, and honestly, the more likely one. Given all the issues we have just discussed, the shaky distance, the questionable cluster membership, and the cosmic dust, it's entirely plausible that the size of Stephenson 2-18 has been wildly overestimated. If so, the star isn't a record breaker that defies the physics. It's just a very, very big red supergiant whose true size got lost in bad data. That other study found much lower luminosity would point to a smaller, more theoretically sound radius. Possibility B: our understanding of the star is incomplete. Now, this is more exciting, more radical possibility. What if Stephenson 2-18 is really that big? What if the measurement, for all its flaws, are basically right? If that's the case, it means that our fundamental rulebook for how massive the stars work need a major rewrite. It would mean there is some more physics we just don't know about yet, and that allows stars to swell to these impossible sizes. And this is why the debate over Stephenson 2-18 it is so much more than just a cosmic pissing contest for the biggest star line. The controversy cuts right to the heart of what we know. Is it an outlier that proves the rule by being a mistake, or is it the exception that breaks the rulebook wide open? Answering that will take better data from better telescopes that can finally nail down its distance and its true nature. So, after all that, is Stephenson 2-18 the largest star in the universe? The honest answer is maybe, but we just can't be sure. The title of biggest star isn't some permanent record carved in a stone. It's a provisional title, an educated guess, written in a pencil with a very big eraser, based on the best but still imperfect data we have. The history of this title is just one king being dethroned after another by new observation. The real story isn't about crowning the champion, it's about messy, brilliant, and deeply human process of science itself. Struggling to measure Stephenson 2-18 shows the incredible ingenuity of astronomers who can try to figure out the properties of an object so mind bogglingly far away. The debates and the uncertainties aren't failures, they are the engine of science. They show us the edge of our knowledge and tell us exactly where we need to look next. The universe doesn't give up its secrets easily. It gives us these cosmic monsters that exist right on the edge of our understanding, forcing us to question what's even possible. And the quest to measure these giants is a testament to our drive to explore, to question, and to try and measure the immeasurable, even if the perfect answer is always just out of reach. If you enjoyed this journey into the mysteries of cosmic measurement, be sure to subscribe and hit that notification bell so that you don't miss our next deep dive into the cosmos. And for another look at the universe's extremes, check out our video on most massive black holes ever discovered. Thanks for watching.